Welcome to Unit 3. Unit 3 is on the mole, and moles are, in this case, are not necessarily the cute, cuddly critters that are blind, but we're talking about moles in terms of chemistry, so we'll see what those in fact are. So the mole is actually a unit devised by chemists to help measure matter, which is what this first section is talking about. So you have to keep in mind that atoms are very, very, very tiny things. There's not an easy way to count them. Remember, we talked about the fact in Unit 1 that you cannot actually physically see them. So we needed a convenient way to discuss the amount of matter present. Yes, sure, we could put things on a scale and measure them by grams, but that doesn't really tell us how much stuff there is. So chemists had to devise a way of doing this. The way you might be able to think of it is when you go to the grocery store, you don't buy eggs individually. If you did, it would take forever, and it'd be a very hard way to go through the checkout if you had to count them individually. So for that reason, grocery stores tend to sell eggs by the dozen. It makes more sense, it expedites the process, and it makes counting a lot easier. So in a similar way, chemists wanted an easier way to talk about how many particles were present. You got to keep in mind, again, these things are very tiny, and counting them individually would take literally forever. And so what we did is we created a unit called a mole. So what is a mole? Well, it's a counting number. First and foremost, let's make sure we're clear about that. This is a counting number. It's how many of something are present. Okay, so it's a little bit different than a unit you've seen before. It's the SI base unit used to measure the amount of a substance. And again, it's counting number. How many physically are present? 12 atoms, 15 molecules. So 1 mole, so this is equal to 1 mole here, is exactly 12 grams of pure carbon-12. And so that's not something very easily determined. And so what we've done is kind of simplified that and said, okay, what that really is, it's 6.022137 times 10 to the 23rd number of particles. That is a lot of particles. That is a huge number of particles. You can't even begin to think about how many that is for a single mole. Keep in mind, we're talking about 12 grams of carbon-12, okay? An amount that might fit, in a couple of palms of your hands, is roughly 6.02 times 10 to the 23rd particles of carbon atoms. That is a huge number. It needs to be such a large number to account for the fact of just how small these particles are. So if we were to upscale this a little bit, let's say instead of carbon atoms, we said that a carbon atom was the size of a marble. Okay, most marbles are 5/8 inch in diameter. If you had 1 mole of marbles, that would be enough to cover the Earth's surface 4 kilometers deep in marbles. Just to give you an idea of the scale of such a thing. So the amount that's fitting in the palm of your hand, if they were the size of marbles, would be 4 kilometers deep on Earth. So visualizing what they look like, over here on the left, this is water. Water's formula, of course, is H2O. Okay, so the red there is the oxygen, and the blues are the hydrogens. One individual unit here, this is a single molecule. Okay, and if you were going to have a mole of them, it's going to end up weighing 18.02 grams. We'll see how that works here in the next section or so. This middle one, there's some copper wiring there. Okay, an individual unit here is an atom. Over here on the far side, this is some kind of a salt. We can probably assume sodium chloride. And here we have a single, what they refer to as formula unit, which would be something like NaCl, 1 sodium and 1 chloride ion there. So each one of those is an individual particle. Well, counting up how many are in this whole copper wire, how many water molecules are in here, would take you literally forever. It's just not going to happen. There's just so many of them. So we've come up with a quicker way of doing the math on that. using conversion factors. That's our solution. So simple problem, something you might do, when you're going to the grocery store. Say you want exactly 5.5 dozen eggs. Well, if they didn't sell them in dozens, how would you very quickly figure out how many eggs that is? Well, this is going all the way back to what we did in the first unit, where we are crossing out units as we go, and we multiply it or divide it by things to get rid of units to get to an answer. Well, in this problem right here, we're going to use a conversion factor of there are 12 eggs for every 1 dozen, or you could reverse this as 1 dozen over 12 eggs. How many eggs are in 5.5 dozen? Well, the unit you want to get rid of here is dozens. That's what you want to get rid of. And you want to be left with the unit of eggs. Well, to do that, you would take the 5.5 times 12 eggs divided by 1 dozen, and that would tell you that that would be 66 eggs. Well, when it comes to particles, down below here, the moles to particles conversion, the conversion factor here is 6.02 times 10 to the, and let's correct this here, 10 to the 23rd particles per every 1 mole. That is our conversion factor. So you have to have this many number of particles, or molecules, or atoms, or formula units, or whatever, is equal to 1 mole. You can have 1 mole of molecules. You could have 1 mole of atoms. You could have 1 mole of formula units. And you got to remember that we can write it a variety of ways. Because it is a conversion factor, you can remember doing this back in the first unit, we can flip which side of the fraction it's on. It can be on the numerator or the denominator side, all depending upon which unit you'd like to get rid of. Okay, particles here, remember we said could be atoms, molecules, or formula units. So we could refer to any of those there. Okay, it could refer to any of those 3. It could be atoms, molecules, or formula units. It's just a counting number. So let's see this in practice. Well, if I want to do this, I got 2.2 moles of sodium atoms, and if the question becomes how many atoms of sodium is that, well, let's just set up what we ought to do. And this is where units are going to be critical for you. Beginning now, you should plan on writing out units with every single number you write down, or you are just not going to be able to keep track of it. And I say that now, and some of you are not going to want to do it. You're going to fight me against, you're going to fight wanting to do it. But ultimately, before the end of the semester, if you don't learn this, if you don't learn to write down the units, it is going to be tough for you to do. So this problem says we have 2.27, and the abbreviation that you'll often see for moles is MOL, moles of sodium. Well, if I want to use this and convert it over to atoms of sodium, I need to multiply it by something with moles on the bottom. Well, we said that that number is 6.02 times 10 to the 23rd particles. In this case, we'll say atoms. Okay, the particles in this instance are atoms of sodium per every 1 mole. So if we take the 2.27 times 6.02 times 10 to the 23rd, okay, we end up getting out of this, and we got to go back to significant figures, don't forget. We've got 3 right here, and this number right here has 3. This bottom number is an exact number. That's exactly 1 mole, so we don't include that. But there's 3 here and 3 here, which means my answer needs 3 of them. This is going to be 1.37 times 10 to the 24th atoms of sodium. And that would be your answer for that. So 2.27 moles of sodium is 1.37 times 10 to the 24th atoms of it. And another problem, if you had 1.17 moles of water, H2O, okay, how many molecules of water is that? Well, once again, we have 1.17 moles of H2O. Okay, and that's how we write it. MOL is the abbreviation that you will see. We need to get rid of the unit for moles. So that's going to go on the bottom per every 1 mole. And that number is 6.02 times 10 to the 23rd. We're going to say molecules this time. Notice it's not always atoms, it's particles. Particles are going to refer to any number of those three: atoms, molecules, or formula units. And we have 1.17 times 6.02 times 10 to the 23rd. And once again, three significant figures in this answer would be 7.04 times 10 to the 23rd, in this case, molecules of water. Okay, if we're going in reverse here, 9.27 times 10 to the 24th molecules of, and I'll rewrite these so you can see them a little bit clearer. This is C6H12O6 glucose. Okay, so how many moles of glucose do we have? Well, we're starting with 9.27 times 10 to the 24th molecules. Okay, we're going to multiply that by some fraction here, our conversion factor. Well, this time I want molecules on the bottom, and I want moles at the top because that's what I'm solving for. So 1 will be up there, and this, of course, will be 6.02 times 10 to the 23rd. This, by the way, and I haven't said this yet, and we should know this, this is referred to as something called Avogadro's number. He's the first guy to come up with that number, Avogadro's number. It's the number of molecules or atoms in 1 mole of a substance. So, in this time, we've got this number on the bottom, which means we are taking this number right here, dividing by this number right there. 9.27 times 10 to the 24th. Divided by 6.02 times 10 to the 23rd. Okay, and if my calculator is correct on this to three significant figures, this is, change back over to the pen, 15.4 moles, which I believe is correct, moles of C6H12O6. Instead of doing these problems here, what I would like to do instead is do a couple on your homework so that you can get these started. So let's take a look at your 3-1 worksheet. So the first section says to calculate the number of particles of each of the following. So this is number 1 on that sheet. We have 11.5 moles of silver. 11.5 moles of silver. And I want to get that into the number of particles. Well, we'll take the 11.5 moles times, I want to get rid of moles, so 1 mole will be on the bottom here, and on the top, 6.02 times 10 to the 23rd. In this case, we have atoms, right? It's silver. Silver is an individual element, so we're talking about atoms of something. So 11.5 times 6.02 times 10 to the 23rd. And if this is correct on my calculator, we should have 6.92 times 10 to the 24th atoms of silver. Be your answer for problem like number 1. If we go down to a problem like number 7, doing this in reverse, it's asking you to calculate the number of moles of each of the following. So 7 says we have 8.90 times 10 to the 23rd atoms of sulfur. And I want to get that into number of moles of sulfur. Okay, it's like my unit for dozens. I want to cut it down into a number that's a little bit easier to work with. Well, the 1 mole's got to be on top because that's the unit we're looking for. And on the bottom, 6.02 times 10 to the 23rd. In this case, we have atoms of sulfur. And taking my calculator there, 8.9 times 10 to the 23rd divided by 6.02 times 10 to the 23rd. And to three significant figures, this is 1.48 moles of sulfur. Okay, so moles are going to be, just looking at our answer here, moles are going to be a generally smaller number than the number of particles. Okay, these should be relatively easy to work with numbers that make sense, numbers that aren't going to blow up your calculator like something like that.